What an exciting time in these live lessons. We've gotten through the drudgery of all of our deep reinforcement learning theory, and now we actually get to put it to use in code and build our own deep Q learning network for winning the carpool game. So the completed notebook is available for you, of course, in the notebooks directory for you to follow along. It's the carpool DQN network. I am going to be rebuilding that for you guys here so that we can talk about it line by line, make sure I don't go too fast over anything. And I encourage you to follow and do the same thing. It'll help reinforce what we're doing here. So I've got a new Jupyter notebook open. I'm going to give it some kind of name like demo DQN. We can add a title. This is going to be a carpool DQN. So the code in this notebook for this DeepQ learner is based on code by Keon Kim, who is a student at NYU. You can check out his implementation by clicking through that link. There is a first step that I've put again at the top of the notebook here, just like for our generative adversarial network. If you're using a machine with multiple GPUs, then you can use this code in the same way that we used it in our generative adversarial network to decide on which devices you want to be running this on. So in our case here, I actually just want to run it on my CPUs. So I'm going to leave this blank here, and this means I won't use any CUDA devices, which means I won't use any GPUs. I want to take a moment to reiterate that this cell here is only useful if you have NVIDIA GPUs on the machine that you're doing this work on. Otherwise, you can ignore the cell completely. All right, the first step for everyone is to import dependencies. So we're going to need something called a random. We're going to use the OpenAI gem, which I showed you guys earlier in these live lessons, to render our environment for the agent to take actions in and receive feedback from. We're going to use NumPy. We're going to use a special kind of list at one point for our for the memory of our agent. We'll talk about memory more later on. We're going to use something called a deck, which is just like a list, except you can add things to the front or the end of the list. And then we get into our Keras stuff. So we're going to use a sequential model to build our neural network for approximating the optimal Q here. We are only going to use dense layers in our network. So the theta weights will simply be the weights and biases of neurons in between layers of a dense network. We are going to use our trusty old Atom optimizer for stochastic gradient descent. We're also going to import OS for creating directories later on, if you didn't happen to do that already in the cell up here. Need Keras models, not model. Let's set some parameters at the top of this file. So it's ideal to have as many hyperparameters as we can at the top of the file. I'm not going to be super religious about that rule this time around, but we are going to define some of our key parameters at the top here. So one of the first things is to define exactly what environment our deep reinforcement learning agent is going to be in. And as we've discussed, this is going to be the carpool game, version 0. So that initializes our environment. There are some hyperparameters related to the size of our state and the size of our actions. So we have 4 possible states in the carpool game: the location of the cart, the velocity of the cart, the angle of the pole, and the angular velocity of the pole on top of the cart. And then we have two actions. So we're just going to create a couple variables here because we're going to use those numbers a lot. And by doing it this way, instead of hard coding in 4 and 2, it makes this code a bit more flexible if you want to switch to a different kind of environment in your own time. So let's define the state size variable. So it's simply, here we go, you can see four possible states like I just said, and action size is going to end up being 2, as I will show. We are going to define a batch size for our gradient descent. We're going to set that to 32. It's a hyperparameter that you can vary by powers of 2 if you want to. It shouldn't make too much of a difference on the outcomes. And then the number of episodes, this is the number of games that we want our agent to play. So you'll see as we get into the code more, the number of games that we play provides us with more data for training. So what we're going to do is we're going to play a number of episodes. Let's say we're going to play 1,001 episodes here. In each of those episodes, we are going to randomly remember some of the things that happened in that episode. And we're going to use that memory to actually train our deep reinforcement learning agent. So we'll see those step by step as we go through. We're going to define an output directory to store our model output. And I've got this line of code here to enable us to create that output directory if it doesn't already exist. All right, that's the preamble. Now we can actually get into defining our agent formally. So we're going to define our agent. We're going to create a Python class to do this. So it's going to be Python class DQN Agent. It's going to have some of its own parameters. So we'll use init to define those. The only parameters that we need to input are going to be the state size and the action size, which we defined above as 4 and 2. So we'll just set those here so that internally they are the same as the parameters that we input. And we're going to define our memory. So remember that I just said we're going to play 1,000 episodes of the game. And on each episode, we're going to randomly remember some of the events that happened, some of the state and action pairs and rewards, and we're going to use those memories and replay them to actually train our model. The advantage of doing things this way is that it prevents us from trying to go over all of the episode and use every single event that happened. That's inefficient, first of all, because events that are closer to each other in time are very similar. They're highly correlated, so they don't provide very much extra information. It's worth it to sample from random spots all over the game, as opposed to a bunch of continuous points in the game. So it's more efficient. The other thing that's great about using memory replay to train a model is that it prevents us from, say we were playing some kind of video game, say even the carpool game, where if the way that our agent started to learn to play, it always moved left first, then we might start sampling only what actions are like on the left. And we might not learn very much about what it's like to go right. So by sampling from all the kinds of episodes that have happened, we get a greater diversity of training data, as well as being more efficient with our use of the training data. So our memory is going to be a deck with a maximum length of 2,000. So remember that a deck is just a list, but we can add or remove elements from either end. So this enables us to keep adding pieces onto our list, but as soon as we get to 2,000, the oldest elements of the deck will start to be removed. So this is more efficient than just building an infinitely sized list, if we're only interested in the last 2,000 memories anyway. Now we have to define some hyperparameters. So gamma is the first one. So gamma is this discount factor. So this is how much to discount the future reward. So as I mentioned earlier when we were discussing theory specifically, the next, when we're trying to estimate future reward, the next time step is easier to guess. We're more likely to guess correctly than 5 or 10 time steps from now. So when we look ahead to estimate how much reward we're going to accumulate based on the actions we take, we want to weight the upcoming actions more heavily than the ones that are in the distant future. So we use this gamma parameter to discount future reward. Another hyperparameter for our model is epsilon. We haven't talked about this yet, but epsilon is really important. So epsilon is the exploration rate for your agent. So there are two kind of modes that your agent can take action with. The agent can either try to take the best possible action based on what it's learned. So this is what we call exploitation of existing knowledge. The alternative to exploitation is exploration. And the reason why we might want to explore instead of just exploit is because the kinds of environments that deep reinforcement learning agents have to explore are often very complex. And if we only stuck with exploiting our existing best practices, then we might not uncover something new that's helpful. This is particularly important because the deep reinforcement learning environments can evolve over time. So in the cart pole game, that doesn't really happen. But in some other kinds of games, or if you imagine a self-driving car, you can get into new kinds of situations where maybe just exploiting isn't the optimal course of action, where it's worth spending some of your time randomly exploring a new type of action. So the epsilon, this is our initial epsilon. So what we're saying here by setting it to 1 is that our initial exploration versus exploitation rate is going to be skewed 100% towards exploration. So at the very beginning of training our agent, we assume, and I think this is the correct assumption, that the agent doesn't know how best to exploit the information about the environment, and so we're just going to explore at the start. However, we're going to decay that epsilon over time. So this parameter allows us to, with ongoing training, we decay our epsilon so that we slowly shift our agent from exploring at random to exploiting the knowledge that it has learned. And over time, this exploitation starts to dominate and we do very little exploring, but we can set a floor on how low the epsilon can go. So we'll set that here. The minimum, so this means that at the very least, even after we've decayed our epsilon all of the way towards 0, the lowest that we'll let it go is to 0.01, which means that 1% of the time, the agent will explore, even, that's the very minimum. So we start exploring 100%. We use the decay to shift that exploration towards exploitation over time until eventually we reach this minimum amount of exploration, which we've set to 1%. Our agent also has a learning rate. This is the stochastic gradient descent learning rate, so it's the step size for our stochastic gradient descent optimizer. And the final parameter to set here within the agent is this build model, which is just a private method that we're setting up here. This means that the method can be used only by this particular instance of the class. Let's define that build model method. So it's in this build model private method that we're going to define our dense neural network for approximating Q star. So this is going to be the usual way that we set up a Keras model. So we're going to use sequential, and the first layer is going to be dense. All of the layers are going to be dense. The first layer, we found that 24 neurons works well. The input dimensions is equal to the state size. So the 4 states of the environment are the inputs into our model. And we are going to set activation to our good old friend rectified linear unit. No surprises there. ReLU is our favorite. In the next layer, we are likewise, of course, going to have a dense layer, and it's going to have 24 neurons. And again, activation is going to be rectified linear unit. That's actually it for our hidden layers. It's a relatively shallow neural network, actually, because now we're going to define our output layer, which has as many neurons as we have possible actions. So this model is sitting here in the middle between taking states as inputs and actions as outputs. So the action size, the 2 possible actions, right or left, are the output neurons, and these are going to have a linear activation. The reason why we have a linear activation is that we are directly modeling these actions. We don't want some abstract probability. We want the action estimates to be direct out of this neural network. Now we are going to compile the model. We have almost always used cross entropy as our cost function. It turns out that for this particular configuration of our agent, mean squared error unusually ends up being a good choice. You're welcome to play around with your hyperparameters and try using cross entropy as well, but it ends up being that given the particular parameters of this specific problem that we're solving, that the mean squared error loss is unexpectedly the better choice of loss. And we need to pick our optimizer, which is going to be Atom. And Atom is going to have the learning rate that we specified up above. Okay, so this method is going to return the model. The next method to define is the remember method. The remember method has a bunch of parameters. So the remember method takes on state, action, reward, next to state, and done as parameters. So this remember method is really important. It's one of the most important bits of how this DeepQ network works well, alongside the memory replay that we're going to go into after we define this remember function. And so this remember function takes in state at the current time step. It takes in the action at the current time step. It takes in reward at the current time step, and it takes in the next state. So it enables us, given a particular state action pair, to model what's going to happen in the next state and what kind of reward we can expect to receive. Done is simply a parameter that lets us know whether the episode has ended or not. The only thing that this remember method is going to do is to append this information into our memory deck. So it's simply going to append the state, the action, the reward, the next state, and done. So you can just copy and paste those in. The next method is the act method. We only really have one more method after this act, which is the replay one, where we do all of the training. Act takes in only the state. So in this method, we are figuring out what action to take given a state. So as I mentioned earlier, based on the epsilon, we're going to either explore randomly or we're going to exploit the existing information that we have accrued within our theta weights of our dense network. So we're going to use the random, we're going to sample a random value between 0 and 1. And if that value is less than or equal to our epsilon, then we are going to just act randomly. So this means that we will simply pick a random action, which in our case means we'll just go right or left at random. So this is the exploration mode. So if we randomly select a value that is less than 1 on the range 0 to 1, then we will take an exploratory action, a random right or left. And then over time, as our model trains, the epsilon will decay, and so we will tend towards exploitation instead of exploration. So how do we exploit? In order to exploit our existing knowledge, we use the theta weights and the predict method on our model. So we pass into our agent when we want to exploit. We pass in state information, and we use the predict method on our deep learning model inside the agent to have a guess at what the best possible course of action is to maximize our future reward. And then we simply return from this method the action that is determined to be the best choice. So that's it. Finally, there's two other tiny little methods after this about loading and saving data. But this one here, this replay method, this is the bulk of all we have to define still within our agent. So the replay method, this takes in as its only parameter batch size. This is really where the action happens, really cool stuff. So the first thing that we want to do is we want to create a mini batch that is a random sample from our memory. So remember, we've been building up this deck of memories with the remember method. You'll see how that happens later. And we're now going to, with our memory replay, randomly sample some of those memories. And the number of memories that we're going to sample is our batch size. And so every one of our memories has a state, an action, a reward, the next state, and whether the episode is done or not. So for each of those values, state, action, reward, next state, done, in our mini batch, if the episode is ended, so if we've either reached the maximum number of time steps that are allowed, which with the cartpole game version 0 is 200 steps, or if we've ended the game by dying, by either the pole getting too large of an angle or by moving the cart off of the screen. If that happens, then we're done. So done equals true. And in that case, there's no mystery about what our target is. Our target is simply equal to the reward. We know how the game ends. We don't need to make predictions about future reward. Target is equal to reward. If we're not done, however, then we have to make some estimates about what our future reward would be, our discounted future reward. So in that case, our target is equal to our reward that we know we get at the current time step plus our discounted, so we use gamma to discount future reward, times our estimates of future reward. And the way that we estimate our future reward is by using our neural network. So here, our neural network, based on information about the next state being passed into it, can predict what the future reward should be. The next step for us here is to map that maximized future reward to the current reward, and we're going to do that with the theta as well. So here we define our estimated, we use our neural network again here to estimate our target given the current state, and then we map that target from the current state to the future state with this line. And then finally, with all of that information all together, we can fit a model to train. So our x's into the model, our inputs into the model are the current state. Our y in the model is the predicted future reward. And so here we're modeling this relationship. We're using deep Q learning to model the optimal Q star. And we only do that for a single epoch because we only really have one moment of information, one single memory to replay here. And we don't want any verbosity because we would just be getting a lot of verbosity output. We're going to decide exactly what we want to output to the screen later on. The final thing to do inside of our replay method is to decrease our epsilon. So with each time step, we want to be decreasing our epsilon. So if epsilon is greater than our epsilon minimum, then set our epsilon for the next replay to be a little bit smaller, decaying it a little bit by multiplying it by our epsilon decay. Okay, that's the end of the bulkiest method. We just have two tiny little methods for saving and loading data so that you can save information and reload it later. Save your model weights. So we just simply have this load method for loading weights, and we define a save method to save those weights for loading later. So there you have it. We have defined our DQN agent. We're now ready to rock to get our agent inside of the OpenAI Gym cartpole environment and train it to perform well at the task, to win the cartpole game.